Good morning, everyone, and welcome to the VinFuture InnovaConnect here in our beautiful capital of Vietnam, Hanoi. Today's event is collaborative efforts between the VinFuture Foundation and the Post and Telecommunications Institute of Technology, marking another important milestone in our shared mission to connect science for humanity. My name is Đức Vượng, and it's my pleasure to be your host today. And to start today's program, let's get a warm round of applause to begin this program. Xin một tràng vỗ tay nồng nhiệt để bắt đầu chương trình của chúng ta. Ladies and gentlemen, for those who are joining us for the first time, a very special welcome. Let me introduce the driving force behind our event today, the VinFuture Foundation. The foundation was created in 2020 with a powerful mission to honor and inspire scientific breakthroughs that create meaningful, positive change in people's lives. At its heart is the prestigious VinFuture Prize, an annual global award celebrating the exceptional researchers and innovators behind discoveries that serve the humanity. And today, we are very honored to be co-organizing this event with the most prestigious institution for information and communication technology in Vietnam, the Post and Telecommunications Institute of Technology, PTIT. As one of the top universities for ICT education, PTIT brings nearly 75 years of excellence to this partnership. The institute was recently ranked Vietnam's #1 for innovation in 2024 SCI Margo Global Rankings. Furthermore, PTIT proudly stands among Vietnam's 5 key national universities, leading the way in engineering and technology. Ladies and gentlemen, joining us today are our distinguished representatives and honored guests from both organizations. Representing our co-host from PTIT, please welcome Associate Professor Đặng Hoài Bắc, President. Associate Professor Dr. Nguyễn Tiến Ban, Dean of Telecommunications and Engineering Department. From the VinFuture Foundation, we are delighted to have Dr. Thái Hà Lê, Managing Director. Dr. Văn Luân Phạm, Executive Secretary. From our partner, please welcome Dr. Crystal Liu, Industry Advisory Board Committee, the University of Sydney. Mr. Tung Hưng, Research Funding Specialist, University of Sydney, Vietnam Institute. Joining them are 3 distinguished speakers who will bring global perspectives and deep expertise to today's discussion. Please welcome Professor Branka Vucetić, the University of Sydney. Associate Professor Di Hoai Linh, Center of IoT and Telecommunications, the University of Sydney. Associate Professor Đặng Thế Ngọc, Research Director, Australia Vietnam Strategic Technology Center, PTIT. Please welcome our guests with a warm round of applause. Xin một tràng vỗ tay nồng nhiệt một lần nữa. And to officially open today's event, we are honored to invite representative of PTIT, Dr. Nguyễn Việt Hưng, to deliver the opening remarks. Xin một tràng vỗ tay nồng nhiệt dành cho Dr. Nguyễn Việt Hưng.
Dr. Lê Thái Hà, Managing Director of the VinFuture Foundation. Professor Đặng Hoài Bắc, the President of Post and Telecommunications Institute of Technology. Professor Branka Vucetić, Director of the Center for IoT and Telecommunications, School of Electrical and Computer Engineering, University of Sydney. Professor Di Hoai Linh, Leader of the IoT Healthcare and Radar Imaging Group, Center of IoT and Telecommunications, School of Electrical and Computer Engineering, University of Sydney. Dr. Crystal Liu, Industry Advisory Board Committee, University of Sydney. And Associate Professor Nguyễn Tiến Ban, Head of Telecommunications Faculty, PTIT. And all the distinguished guests, esteemed representatives, valued faculties and students, ladies and gentlemen. Good morning and a very warm welcome to PTIT for InnovaConnect 2025. It is a profound honor and a moment of great pride for PTIT to host this significant event, a cornerstone of the InnovaConnect series, generously supported by the pioneering VinFuture Foundation, whose commitment to promoting scientific and technological innovation for the greater good align perfectly with our core mission at PTIT. PTIT is proudly to be chosen as one of the 5 key universities in science and technology in Vietnam. We extend a special and heartfelt welcome to our distinguished guests from the University of Sydney and also the representative from the University of Sydney Vietnam Institute. Your presence here as an academic leader from one of the world's most innovative institutions is not only an inspiration, but also a very powerful affirmation of the potential of global academic collaboration. The InnovaConnect series is a VinFuture Foundation initiative that connects the world-leading minds with Vietnam's science and technology community, fostering academic exchange and collaboration toward new breakthrough. In this spirit, we are proud to co-organize today's VinFuture InnovaConnect event with the title, The Role of IoT and 6G in Shaping the Architecture of Next Generation Covers Communication Network. This section continues the mission of InnovaConnect by sharing the latest research trend and innovation in 6G, IoT, and intelligent communication, while discussing frameworks that address the evolving needs of industry, urban system, and society. As the leading university of technology, we understand that the future of Vietnam and the world is linked to advancement in telecommunication, computing, and digital transformation. Our role is to be the incubator where talent meets technology, shaping the young minds who will build the future. This is why the triangular partnership represented here today with PTIT is a national technological strength. The University of Sydney is the global academic excellence, and VinFuture, the visionary support. This partnership is so crucial. It provides the perfect platform to transform theoretical insight into tangible real-world solutions. I urge to all our students, I urge you and all the faculty members to engage actively and maximize this unique opportunity to learn from world-class experts. Let InnovaConnect 2025 be more than just a series of lectures. Let it be the starting point for new joint research projects, exchange programs, and lasting friendship. Let us commit to utilizing our collective intellectual capital to address the challenges facing humanity. Our thanks once again to VinFuture Foundation and to the University of Sydney professors for your generous effort. May the conversation we have today spark profound ideas and illuminate the path to a brighter and more connected future. I wish you all a highly successful and inspiring InnovaConnect 2025. Thank you.
Thank you very much, Dr. Nguyen Viet Hung, for your wonderful words. And now, may I invite Dr. Thai Ha Lê, Managing Director of the VinFuture Foundation, to deliver the welcoming speech on behalf of the foundation. Please join me in welcoming Dr. Thai Ha Lê to the stage. Xin một tràng vỗ tay nồng nhiệt dành cho Giám đốc điều hành quỹ VinFuture.
Associate Professor Đặng Hoài Bắc, President of the Post and Telecommunications Institute of Technology. Good morning, distinguished professors from the University of Sydney, scientists, colleagues, and guests. It is my great pleasure to welcome you all to today's VinFuture InnovaConnect event, co-hosted by the VinFuture Foundation and the Post and Telecommunications Institute of Technology, PTIT. This morning, we gather under a timely and visionary theme, the role of 6G and IoT in shaping the architecture of next generation's converged communications network. On behalf of the VinFuture Foundation, I extend my heartfelt thanks to PTIT leadership for their close collaborations, to our distinguished speaker from the University of Sydney for joining us from Australia, and also guests from across the world, and to all participants here in Hanoi and online from many countries. As we look towards the 6G era, we are witnessing the convergence of artificial intelligence, the Internet of Things, and next generation's wireless technologies that will redefine the way our world connects. From millimeter wave communications and massive MIMO system to reconfigurable intelligent surface, open radios, access network, and AI-driven automations, these innovations are not merely technical milestones. They are the foundations of a more intelligent, sustainable, and inclusive future. We are truly honored today to welcome three distinguished experts whose pioneer research embodies this vision. Professor Branka Vucetic, Director of the Center for IoT and Telecommunications at the University of Sydney, an internationally renowned scientist who has shaped the global evolution from 4G to 5G and now to 6G. Her visionary work in wireless communications and coding theory continues to inspire new generations of researchers worldwide. Associate Professor Tu Huailing, also from the School of Electrical and Information Engineering, the University of Sydney, whose cutting-edge studies on AI, OT, and digital health are opening new frontiers for intelligence, human-centered applications that bring technology closer to the needs of the society. And Associate Professor Đặng Thị Ngọc, Deputy Director of the Institute of Information Technology and Communications at PTIT, one of Vietnam's leading experts in network engineering, who has been instrumental in shaping national research and education in telecommunication as smart system. We are deeply grateful for your participation and look forward to your insights on how we can architect the future of technology and connectivity together. At the VinFuture Foundation, our mission has always been to recognize and promote breakthrough science and technology that creates a better life for humanity. Through the initiative like the InnovaConnect, we aim to build the bridges between global experts and local innovators, between cutting-edge ideas and practical application, between applications and realizations. We believe that the future of technology must not only be advanced, but also ethical, inclusive, and sustainable. And it is through open dialogue, collaborations, and shared purpose that we can ensure the breakthrough of the 6G era will serve not only the connected few, but the collective many. I hope today's discussion will spark new ideas, new partnerships, and new pathways for Vietnam and the world to lead together in this transformative journey. Once again, my deepest thanks to our esteemed speaker, our partners at the PTIT, and all of you, the students, researchers, and innovators who are contributing to this exciting new chapter of scientific progress. Thank you very much. I wish this discussion very fruitful and successful. Thank you very much.
Thank you so much, Dr. Thai Ha Le. And now, before we begin our discussion on the role of IoT in 6G shaping architecture of next generation converged communication networks, let's take a moment to watch a short trailer that gives us a glimpse of today's topic and inspiring speakers who will share their insights. Please welcome.
Over the past decade, breakthroughs in science and engineering have driven telecommunications into a new era. The age of 6G, networks nowadays do more than transmit data. They sense the environment, process information, make decisions at the edge, and support highly distributed, intelligent control. From remote healthcare and autonomous transportation to smart grids, responsive cities, emergency services, and digital access for underserved regions, next-generation hybrid networks promise an unprecedented leap in societal capability. Yet unlocking this vision requires more than technological breakthroughs. It demands a highly integrated 6G IoT ecosystem and deep international collaboration to accelerate research, talent development, and knowledge sharing. In that spirit, the VinFuture Foundation, in collaboration with the Post and Telecommunications Institute of Technology, PTIT, presents InnovaConnect 2025, themed The Role of IoT and 6G in Shaping the Architecture of Next-Generation Converged Communication Networks. This event introduces cutting-edge research and architectural models capable of supporting the rapidly evolving demands of industry, modern cities, and broader society. Joining us is Professor Branka Vukotic, a leading researcher at the University of Sydney, Australia, specializing in wireless communications and IoT. She is widely recognized for pioneering contributions to error control coding and URLLC, earning prestigious distinctions including the ARC Australian Laureate Fellowship and fellowships of the Australian Academy of Science, ATSE, and IEEE. Accompanying her is Associate Professor Zihui Lin from the School of Electrical and Computer Engineering, the University of Sydney, Australia, whose research focuses on 5G, 6G systems, RIS, RHS, wireless AI, and AIoT-driven digital health. He has authored 2 books and over 300 publications in IEE journals and conferences, and holds 16 granted patents, making him an influential contributor to advanced wireless network technologies. From Vietnam, we are honored to welcome Associate Professor Thi Ngoc Dang, Vice Dean of Telecommunications and Head of the Wireless Systems and Applications Lab at PTIT, focusing on optical wireless communications, FSO, radio over fiber, and quantum key distribution, QKD. He has authored and co-authored over 140 publications, led 10 national and ministerial research projects, and achieved Vietnam's first FSO-based 4K UHD video transmission, alongside regional collaborations funded by ACNIVO and APNIC. As 6G converges with IoT, connectivity becomes intelligent, autonomous, and universal. Together, these breakthroughs will shape a communication fabric that is more powerful, more inclusive, and deeply aligned with human needs. Join us in Hanoi for InnovaConnect November 2025, where global experts chart the future of hybrid networks and unlock what comes next. Together, we connect the future.
And now it is my great pleasure to introduce our first distinguished speaker, Professor Branka Vukotic from the University of Sydney, Australia. Professor Branka will deliver the presentation on Beyond Channel Intelligent Wireless Network of 6G. Please join me in welcoming Professor Branka Vukotic to the stage.
I first would like to thank my host from PTIT and from the VinFuture Foundation for inviting me and hosting this event. And this is my first visit to Vietnam and PTIT, and I hope it will be just the beginning of our long-term collaboration between our institutions and a long-term friendship. So my topic today is Beyond Shannon Intelligent Wireless Networks for 6G, where I will introduce a new theoretical framework for designing wireless communication networks, present some examples using this framework for the design of the physical layer for the next generation wireless networks, 6G. Wireless communication networks are a key pillar of modern communications. Wireless traffic amounts to 60% of the total network traffic, and it is increasing rapidly, driven by IoT applications. The most prominent wireless networks are cellular wireless networks, which developed over several generations of wireless standards. For example, 4G was all about connecting people, while 5G extended connectivity to machines. Now we are working on 6G, which will be an intelligent platform, not only connecting people and machines, but also integrating communications, sensing, control, localization, and AI computing. With these evolutions, the demands for KPIs, key performance indicators, like data rate, reliability, latency and network have been increasing constantly. And for example, it is expected that 6G will have KPIs by several orders of magnitude improved compared to 5G. And this is where the research challenge comes in. The current theories and technologies are unable to support this growth in KPIs. So this is what my talk will be about, how we are going to make this leap to 6G when we don't have the theories and technologies that can support this growth. So we need to come up with a new theoretical framework that can enable this growth in performance indicators. So just to remind you of the Shannon's legacy, so the Shannon communication theory and communication model served as the cornerstone of the communication theory and development in the last several decades, in fact over 70 years. And they provided fundamental insights into channel capacity and error performance, and served as the foundation for developing of innovations like turbo and LDPC codes, which approach the channel capacity that was predicted by Shannon, and also spectrally efficient methods like OFDM and massive MIMO. All these technologies enabled increase of data rates from, for example, bits a second to multiple gigabits a second in 5G. So the Shannon model, which is the basis of representing communication systems, is shown here, and it consists of a sequence of signal processing modules like source encoder, channel encoder, modulator, and the corresponding modules at the receiver. These are the underlying assumptions of the Shannon model. First, according to the Shannon theory, we assume that the network delay can be infinite, that we can tolerate infinite network delay. Second, it is assumed that these signal processing modules shown here are independent between each other, and they could be optimized and designed separately from each other. Third, it is assumed that the channel here, the physical channel here, radio channel, can be mathematically modeled. Usually it is Gaussian. And finally, it is assumed that Shannon model is about bit transmission. So we transmit only bits rather than meaning, which could be another approach in 6G. Now, when we move to 6G, those assumptions from the Shannon model are no longer practical and applicable to new types of networks and communication systems. First, this assumption of infinite delay could be tolerated in human-to-human communications, which was 4G. They are no longer relevant in 5G, even let alone 6G. In 5G, we already started working with connecting machines, and machines are much faster than humans, and for them, we have to have very low and very strictly defined network delay. It could be in 1 millisecond for 5G and even much lower than for 6G of the order of microseconds. Then the assumption of independent of signal processing blocks is no longer valid, because in 6G we are going to have strong interdependence between, for example, channel coding and source coding, between the modulation and channel coding. And there will be new applications which will introduce dependence between control and communications. And this assumption of independent signal blocks is no longer valid. So we would achieve much better performance if we treat them as a single block and optimize them together. The third, the assumption of mathematical tractability of the channel. While we could actually model accurately some communications media, in particular massive MIMO, which has been already mentioned here in this event, that is a very powerful multiple access scheme that was introduced in 5G. For that system, strong interference between transmitted signals, and interference cannot be modeled by analytical methods. So that means this assumption does not hold for systems in 5G and 6G. In using analytical methods for dense and heterogeneous networks, in order to use a very good maximum likelihood algorithms, their complexity increases exponentially with the number of users and the number of nodes in the system. So in practice, they become too complex and cannot be used. And finally, in order to achieve such high data rates in 6G that would support augmented and virtual reality and industrial control in real time, we have to have much higher data rates. And in order to achieve such higher data rates, and we already have maximum, we are at the top of the Shannon capacity limit, we have to do something else. So transmitting bits only is no longer valid. So in 6G, we have to focus on transmitting meaning rather than bits. So this is something which is beyond the current Shannon model and Shannon theory. So it is clear now that we have to have a new theoretical model for the design of 6G networks. Auto-encoder end-to-end AI-optimized methods have been successfully used in data compression and pattern recognition. Recently, these methods have been introduced in communication. However, there are certain problems with their application in communication. So what is this autoencoder approach in replacing the Shannon model? So the whole sequence of signal processing in the transmission is replaced by one network, and the same sequence in the receiver is replaced by another neural network. And all these signal processing operations are done in a single step in one neural network rather than in a sequence of communications modules. The advantage of this system, first compared to the Shannon model, is that because the system is trained by learning, by deep learning of these neural networks, so that instead of having the analytical models for modeling the channel, we'll learn from data. So we learn from the actual measured data about the characteristics of the channel. So we don't need analytical models as in the Shannon model.
Excuse me.
Okay, thank you. Yeah. Then these neural networks are jointly optimized between the transmitter and receiver, and by doing that, we increase the performance, we increase the reliability, and we increase also the spectral efficiency of the system. And another important feature of this system is that instead of transmitting raw bits, we transmit meaning. So we focus on critical meaning parts of information. So we give more bandwidth to those important parts of a message. So we transmit meaning rather than raw bit data. So advantages of these systems are reduced delay because we do the whole transmitter in one single operation rather than going from one module to another. Then improve the performance, reliability, and spectral efficiency because of joint optimization. Also, once the system is trained, then the inference in real time is simple and its complexity is low. However, there are big challenges in using this model directly in telecommunications. First, it requires high training complexity. So communication networks, in particular massive MIMO, generate data with high dimensionality. So each antenna, each user, each time slot add to this dimensionality. And the training complexity is an exponential function of this dimensionality. So in applications, this is just too complex to be used. Then there's no scalability. So that means we have to train this model for each signal-to-noise ratio, for each number of receive antennas, for each number of transmit antennas, for each signal-to-noise ratio, for each code word. So it is absolutely too complex to scale up. So in certain methods, if you train it for one value of a feature, then you don't need to train for others. But here you have to train them for all other applications. Then something characteristic for general AI methods is that there is no optimality guarantee. So those who work with AI know that we talk about hallucinations of AI methods. So AI methods sometimes can just give wrong results. Another important feature is that these systems are not compatible with the current standards. So that is a very practical limitation in using such systems. So this is our proposed approach to go beyond Shannon. So we are applying AI-augmented hybrid system design, which combines deep learning with the analytical communication theory methods. So instead of going directly from the Shannon model, replacing all signal processing modules with a single neural network, we enhance each of these modules by deep learning. And by doing this, we actually preserve the Shannon infrastructure, which means we preserve the compatibility with the current communication standards 5G and 4G. Then we integrate adjacent blocks into AI deep learning models, into a progressive pipeline, and then this could lead to the optimum autoencoder end-to-end optimized model once we have enough data for training and enough computing resources to do it. So one important feature of this system is synergy between analytical methods and deep learning. Deep learning is very good in capturing nonlinear and complex relationships in data, which analytical models can miss. However, graph-based analytical models are much better in modeling the structures and relationships, And when they are combined together, then they can achieve better accuracy and shorter training and also better convergence. They can guarantee, if not optimality in each case, they can guarantee performance. And they are also, once trained, they are very simple to implement. And importantly, they are compatible with the current infrastructure, 4G and 5G. We also here use semantic communications. So we introduce the convergence of source and semantic codings, where semantic encoders at the transmitter encode data into semantic features, and at the receiver we use large language models to reconstruct the transmitted messages. So now I will show how we apply this theory to the design of the physical layer in 6G. So here we will show first how we apply the proposed AI augmented hybrid model to the design of detection in massive MIMO, and then we'll show how we apply the model in design of the channel coding. Then we will show semantic communication with combined channel coding and semantic coding and error correction. And here we apply that also to joint design of communications and control. As I said, 6G is going to be integration of communications, sensing, control, localization, AI computing. And the first step, because we cannot design it immediately, all of them together, as the first step is design one by one. And so we apply this to the design of communications in control, but because due to time limitation, I will show just the first three instead of this one. So this is the system that I'm going to show here, how we enhanced. So this is first how we enhanced the modulation and demodulation in massive MIMO. So this is the model that we consider here. So it is the massive MIMO system, which consists of NT independent mobile phones, and at the base station we have NR antennas. So in order to achieve high spectral efficiency and high data rates, these phones transmit at the same time in the same frequency. So they all transmit and interfere with each other. So the role of the receiver is to separate them and get clear messages. In theory, you can separate them by using maximum likelihood methods. If you have the maximum number of users equal to the number of antennas at the base station NR. However, these maximum likelihood methods are very complex. They grow exponentially with the number of mobile phone users, and in practice, when you have in 5G several hundreds of antennas, and in 6G several thousand, it is absolutely impractical to implement. So in practice, we use MMSC receivers, which have polynomial complexity, but the performance is not good. So I will show only the results of applying our AI methods combined with analytical methods for the detection, separating those interference signals and getting clear signals at the receiver. So here we have, we model both the modulator and demodulators by graphic neural networks. So here we combine graph-based modeling of received signals or received antennas, and then using graph neural networks to enhance them with deep learning. So in each node, where each node represents the estimation of the received signals, we embed a deep learning neural network and we also use the message passing analytical method. So we combine deep learning with two analytical methods. Graph-based representation of users, which is capturing the topology of the network, and message passing analytical method. And by using that, we obtain here the results. So the red curve is an MMSC, the standard receiver that is used now. The black one is the maximum possible performance, and the blue one is the performance that is achieved by our AI-enhanced hybrid model. So you can see that it actually approaches the performance of a maximum likelihood, which has exponential complexity, with a receiver which has similar complexity as MMSC, and even for the maximum possible number of interference, 64 the transmitter and 64 receiver. So this is patented innovation, and which has been implemented in our software defined networks at the University of Sydney. So this is another application in channel coding. Channel codes are used in order to correct errors that are caused by transmission in real channels. Conventional channel codes are very long according to the Shannon theory, because Shannon theory to achieve the channel capacity requires very long codes. However, for ultra-reliable low-latency communications that we need in industrial control and self-driving cars, we need to have low latency, which means that these long codes are not acceptable. So in 5G, LDPC, long LDPC codes and belief propagation are used. However, they have very poor performance for short codes that are required for URLLC. So here are some existing autoencoder channel codes which use only the standard neural networks, fully connected FNN, or convolutional neural networks, CNN, or recursive neural networks, and they don't use analytical methods at all. So our method is combine analytical methods with deep learning in order to improve the performance. So by using this principle, and so that's jointly designing the encoder and decoder, where both the encoder and decoder are represented by graph neural network, graph to capture the topology, and then combining it with the belief propagation analytical methods of decoding. We designed better codes and better decoding methods. So here are the performance. So here we have the blue curve, the upper one is the conventional BCH code, which is a good code for short codes. And then when we use only GNN-based decoder, we achieve an improvement of about 2 orders of magnitude. And then when we do jointly design of encoder and decoder, we achieve a further, that is the next below a red curve, we achieve further improvement by 1 order of magnitude in the error performance. And now, finally coming to semantic communication. So, as I said, in 6G, we are going to make a major leap from Shannon model to semantic communication, where we transmit not only raw bits, but we transmit meaning. So here in the traditional communications, we use raw data and as the input to a source encoder. We transmit raw data into bit format, and then we further protect them with channel codes and modulation and transmit over the physical channel, and at the receiver we have corresponding modules for processing. So in traditional communications, we transmit only bits, and we try to perfectly recover bits. So all bits are equally important for us. However, that is not efficient, so in the future we have to focus only on transmitting important information and ignoring the parts which are not important. So that is the essence of semantic communications. So the current semantic communication systems ignore channel coding. They only compress. In that way, they become even more sensitive to errors in the channel. So what we do here, we actually introduce channel coding and design new channel codes which are suitable for semantic communications. So the main challenges here are efficiently extract semantic information, then design new channel coding which have semantic awareness, and importantly, stay compatible with the current system. Because without that, no one would accept our system and no one will implement them. So, in traditional bit-level systems, an entire message is encoded as a long code word according to the Shannon theorem. So, for example, if we transmit this code word, machine learning is very powerful, this sentence, it will be converted to a bit format and protected by a long channel code. So this is a very good code for long code words because it can achieve the channel capacity. However, in the rare events, when the signal-to-noise ratio is low, then the whole decoding information message will be corrupted. So if we transmit machine learning is very powerful, what we receive is just incoherent message below, and there is no semantic context to recover this message. So in our method, we first do semantic segmentation of long blocks. For example, for this sentence, we segment this message into words. So the one word is machine, the other is learning, then the next one is very, because these are short words and powerful. If the decoding fails, only one of these blocks will be corrupted. So that means we will have only one of these blocks which is corrupted. So to protect the sequence by channel codes, we now encode each of these segments with a short block code to be consistent with URLLC in a parallel channel encoder in order to reduce latency. And then we transmit them over the physical channel. If the decoding fails, it could be, for example, only one block in error, and then we can recover this code word from the semantic context by using semantic error correction based on the large language model. Here we use a large language model which stands with bidirectional auto-recursive transformer. In order to improve this system, we added one more feature of this algorithm so that the semantic decoder does not give only one most likely word, it gives a list of likely words, and then we combine this list with the channel likelihood and select the information with the highest likelihood. So in this case, for example, if we have this is transmitted sequence machine learning is very powerful, then the last block is in error, then we get a list of decoded words, and then if we combine them with the channel encoding likelihood, then we get that the most powerful is the one powerful, the most likely is powerful, so we can recover the original transmitted sequence. So in terms of the performance, if we compare the performance of these systems, when we encode them with only channel codes, with long codes, as it is done in traditional systems, and these two new codes, in terms of the bit transmission, the new systems have only minor improvements at low SNRs. However, if we use another performance criterion which is used for semantic communications, it's called Rouge, which shows how similar is the decoded message to the original one in terms of meaning. We get significant improvements here by more than 50 times for low SNRs when the problems occur. So if we transmit, instead of text, if we transmit images, so here we have original image, we have one with no coding, we have one with 2 blocks, but then if we have 8 blocks, when we have segmentation into shorter sequences, we get a perfect result by using this method. So the conclusion here is, for bit communication, it is okay, it is good to use long codes. However, for semantic communication, we have to use short codes and segmentation in terms of meaning, so then we achieve much better results. So this concludes the theoretical part and design of the communication network physical layer by using the proposed method. So now I will show our new technology which can be applied for IoT in mining and in agriculture. So you all know the Wi-Fi. The methods that I showed could be used not only in 6G, but in all communication networks, in Wi-Fi and in satellite communications. And the current Wi-Fi has only a range of less than 100 meters, and it is used only indoor. So another big problem with the current Wi-Fi is that the latency, network latency, is random, and it is high, in particular for industrial control or self-driving vehicles. So there is a growing need for Wi-Fi with high range and with lower latency. And we have developed such a solution where our Wi-Fi can have long range, in particular in tunnels and in open areas. Instead of 100 meters, we can reach kilometers. Then it can achieve high data rates as the standard Wi-Fi. It is compatible with the standard Wi-Fi. Then it is already applied, so our technology is patented and has been applied in mining, in underground mines, where it can replace the standard Wi-Fi in order to reduce the number of access points and reduce the cost. And other possible areas are in broadband communications for rural areas. Australia is a vast country, and our rural areas and outback areas have no internet at all. And it can be used in emergency services, in agriculture, in defense, and can also be used for industrial control because of low latency. So the competing technology is multi-hop Wi-Fi. So the problem with multi-hop Wi-Fi is that it has high latency and high cost because you have to have a large number of access points. Wi-Fi Hello works in the band of 900 megahertz, so it is not compatible with the current Wi-Fi, which is a big problem. And it also has high latency. And our technology has high range, high data rate, low latency, low cost, and Wi-Fi compatibility.
Thank you so much, Professor Brancavusseri, for your great presentation, enlightening insights. And now it's my pleasure to introduce our next distinguished speaker, Associate Professor Zhi Hua Lin from the University of Sydney, Australia. Today he will be speaking on Artificial Intelligence of Things, IoT for Digital Health. Please welcome.
Okay, so welcome to my presentation, which is titled Artificial Intelligence of Things for Digital Health. So this is the outline of my talk. First, I will briefly introduce the artificial intelligence of things, from the motivation to the architecture and the research challenges. And then I will simply try to explain our current research in this area. And then I conclude with the future research directions. The motivations for the artificial intelligence of things actually comes from the many factors. Here I just list about 4 of them. And the first thing is that the rapid expansion of the medical device actually enables continuous monitoring of the healthcare outside the hospital settings. Okay, so the expected, the number of the digital device by 2030 can up to 1 billion, which results in petabytes, digital medical data per day. So this definitely motivates the development of artificial intelligence of things. And also, the modern, the mobile health apps, home monitoring, etc., which enables, the healthcare from hospital-centric, reactive, towards to patient-centric, and proactive, predictive, and personalized care. So this also motivates the development of the AIoT. Okay, and also the development of 6G, the features for terahertz communication, sub-milliseconds latency, which enabled by 6G, made some applications such as latency sensitive applications like telesurgery, okay, possible. This enables the ultra reliable, ultra low latency artificial intelligence of IoT. So combined together, so this motivates the development of the advanced artificial intelligence of IoT. So what is AIoT? AIoT actually is a combination of the AI and the Internet of Things. So actually it is a fusion of cognitive intelligence of AI and the pervasive connectivity of IoT. So it transforms, from a network of sensing device to a, intelligent ecosystem. In digital health, actually, it transformed from simple, data collection, data monitoring, to the diagnostic, reasoning, prediction, and also personalized healthcare. Generally, the AIoT contains the following parts, the data source, data processing and management, and also application-based analytics, and also the applications. So the data source, such as the sensors and also social media devices, they produce the raw data and then processed in the data processing and management units. And the output goes to the application-based analytic modules, which is powered by include the procedures like data discovery, data exploration, and the decision management, and also the predictive analytics and modeling. So the generated outcomes goes to the application. Application could be the clinical dashboard, to just show the results. From the, across the data source, from the data source to the application, actually, is coupled with this data security, privacy, and also the governance management. So the research challenges in IoT here actually is quite many, so I list a few of them. So the first is data heterogeneous and quality. IoT data, particularly for the biomedical IoT device, they collect different diverse type of data, such as the biosignals, imaging, environment-related data, and from maybe noisy environment, and also with adaptive sampling and etc., which results in the data heterogeneous distribution. And also the edge intelligence actually performed in the device or edge device, which has a very limited resource. Okay, so therefore low complexity like light model, AI models, it becomes important. This is a very challenging problem. And also, for the federated and the distributed learning, the data usually are non-IID. It's non-independent, analytical, distributed. So this will result in convergency and also the, bias issues from the federated learning. And another two questions actually related with the communication, like, the dynamic and unreliable connectivity, because, data collected based from heterogeneous networks, such as, Bluetooth, Wi-Fi, 5G, 6G. So the quality of collected data might be not very reliable, and sometimes may missing the data. And also for some applications, like, latency sensitive things, so this requires, it has a strict latency requirement. Okay, so actually this is a very challenging problem. And the last one, which I'm going to mention, is about privacy, security, and the trust. Continuous long-time monitoring, it will generate the privacy and security issues. So we just discussed, the AIoT. So here we just, briefly explain what is our current research in the area of AIoT and also in the digital health. So we work with communications for AIoT, and particularly we'll focus on the meta surface, for 6G. And also we work with ambient backscatter communications. So this is mainly for the battery-free, okay, energy efficient applications. So this could be the next generation, the RFID. So basically the device has no battery, no power. And then in the digital health regime, we work with a number of different healthcare projects, such as ECG, AIoT. I will explain a little bit more in detail. And in this area, we work with the atrial fibrillation diagnosis, and also we work with the prediction. Okay. And besides this, we also worked with the emotion detection recognition based on the ECG signals. And also, besides this ECG-based AIoT, we also worked digital twin, for the particularly for the dementia, prediction. So from the communication side, our focus is on the reflective intelligent surface, and also we work with reflective holographic surface and the telephone communications. So besides the the work which we are going to I'm going to discuss, actually we also work with channel estimation, integrated sensing and communications. Okay, so what is reflective intelligent surface? Actually, RIS is a array which composed of a large number of the sub-wavelength elements. Each element actually they can receive the incident waves and then do reconfigurable for the wireless environment. So therefore, it can increase the transmission throughput, reliability, and etc. So the rays can be used for range extension, and also can be used for the physical layer security and power transfer, and it's also enabling technique for D2D, device-to-device communication. So in the wireless communication system, if we introduce rays as a mean to help for transmission, actually the rays can help, overcome the blockage, and so therefore the improve the transmission, quality, and also it can enhance, the spectral efficiency and energy efficiency. So our research folks actually, in this work, we just try to give some explanation about the RIS-aided, finite block length transmission, okay, for short packet transmission. Okay. We try to derive the, achievability bounds and also the converse bounds, okay, for particularly the RIS-aided wireless communications. Okay. So why this question is important is because, the current research, the current research actually they have the analysis for the capacity performance, but it's in the region of assumptive, which means they analyze the performance when the input of the data has infinity long. Okay, but in reality, particularly for IoT applications, the information usually a short package. So this kind of assumptive capacity actually cannot give you a tight bond. So in our work, we just try to derive this a tight convergency bound and achievability bounds for the RIS-aided channels, particularly for finite block length transmission. So the system model which we studied is is given here. So we have a transmitter and we have a receiver. There is no direct link between the transmitter and the receiver. So there is something blocked in between. And we have to rely on the rays, okay, to provide the reliable transmissions. And both the transmitter and receiver, they equipped with multiple antennas. So what we did here is that, so just to give you a general knowledge about what is the achievability bounds. Achievability bound actually is just a lower bound on the code rate. The code rate is same as the code size n. I mean the k divided by n is the information divided by the code word length, and the equivalent is the you just determine the code size. Okay, for a given code word length and the error probability. And the converse bound is just to give you an up bound. So for the code word size, for a given code length, and also the error probability. So the matrix which used is mutual information and information variance. Okay, it's based on the Shannon theory. So our results is given by this. So the rate actually can be lower and up bounded by the two items. Later on, I will show you actually this gives a tight bond for short block lengths. So the analytic tools, we used to derive these achievability bounds and converse bounds is based on the Berry-Eason theorem and the DT bounds, and also this gives achievability bounds, and also the binary hypothesis testing and plus auxiliary channel models gives the converse bound. And because the bond is very complicated, so we have to use some kind of a tool to try to approximate. So this can be based on the Taylor expansion saddle point method to simplify the integrals, and also we use some method to simplify the mutual information and the information variance. So this we gave some, just some numerical results, which for some particular sightings. And this sighting, actually, we have a 2x2 memo, and in between, there is a race. The race has, the left one, they have 16 elements, and in the right one, they have 32 elements. Actually, from the, numerical results, the bond, you will see that the bond is very tight, okay? Both the up bound and the low bound, actually, the coincidence, almost a coincidence, when the block length goes to a little bit longer, okay? And also, we studied the different channel types and also the phase alignment, okay? We studied the relay fading, reshape fading, perfect phase alignment, and also imperfect phase alignment. And generally, our finding is that in terms of the required block length and rate performance, region fading actually gave a better performance compared with the relay fading. And for the phase alignment, perfect phase alignment, of course, is more complicated. Okay, gives a 20 dB signal noise ratio gains compared with misalignment. We also, try to verify using the practical codes to verify, to validate our bonds. So we studied different memo situations, and then we plot the beta error probabilities against the simulation results for Polar codes and also extended BCH codes, and you will see the performance can be perfectly bounded by the up bound and the low bounds. Okay, so above is just a communication side. So the next is about the ECG IoT. So the problem, is that conventional, ECG signals, if the people suffer from this kind of a heart arrhythmia, they go to the hospital. They generally, the doctor recommend you wear halter. Halter, is inconvenient to wear and uncomfortable. So you can wear at most, usually 24 hours to 48 hours. And so our solution is that we try to develop a single lead, lightweight ECG device, and also we developed the real-time automated diagnosis system for heart arrhythmia. So this is the hardware which we developed. The up one is the first generation, and the lower part is the current version. Okay, is the new version. So you will see that both of them, they have a long time wearing. It can be wear for the first generation can be wear for 7 days, and for the second generation, actually both of the device is supported by rechargeable battery. Okay, and per charge we can, for the first generation is 7 days, and for the second can be up to 14 days, more than 15 days, 2 weeks. And in fact, it can be very long time. as long as if no power, then you just recharge it. So the device, these are some characteristics for the hardware, like, it has 24 bits ADC and also 250 hertz sampling rate. So the device contains 3 units. Actually, it's 4. Okay, so this is true for all the sensor nodes. Okay. So the first is the sensing units, and then the processing units, and also the wireless transmission units. The fourth one is actually the power supply. Okay. And for the sensing units, the normal thing is that the electrode. We try to develop the skin-friendly electrodes. Okay. And so the patient, when they wear the device, they feel comfortable. And for the wireless transmission, we use the BLE. This has low power consumption. And we also developed an AI engine which can automatically analyze for the ECG data which are obtained from the ECG device. And then automatic result, it can automatically produce a digital report. Our work actually, this is, in comparison with the existing device like a zero patch, this is a very successful commercial product, which is very popular in US markets. And the advantage for our device is that we can wear for a longer time. Also we are rechargeable, but for zero patch, actually it's just a one time. Okay. So after you wear, you have to post it back to the manufacturer. They have to, analyze this manually, and then they send the letter to the patient. So in fact, they cannot do the real time. And our case, we can do the real-time data transmission. So this is the thing. So our solution actually builds a completed, process model. Okay, we can provide, from a data monitoring, data, collection to the complete. The service management, okay. Service management. So our model actually can transform, the traditional patient to doctor connection to the complete, data-driven, the disease management system. So our single lead ECG, system actually, is a closed loop which contains 4 steps. In the first step is the patient side, and the second step is the cloud side, and the third one is the physician, cardiologist. So this is, intervened by the human being. And the first one is called continuous learning. Okay. So in the device side, the device generated the ECG signal and then send through the mobile app to the cloud. Okay, the cloud generates the the reports, for the professional heart arrhythmia, the reports, digital reports, and then send to the physicians, cardiologists. The cardiologist review and also confirm the report, and then they can send back to the patient. So you will see our reports actually is not through the AI, okay? It also is produced by AI, but actually it's validated by the doctors. So you can make sure that the report is very reliable. And the doctors, after they do review and also the confirmation, they will send the validated data to the continuous continuous learning module. Okay, the continuous module, okay, based on the validated data set, they do the data set expansion and the model optimization. Okay, so eventually they form a closed loop. Besides the single lead, we also work with the 12 lead, the ECG signals. The 12 lead actually, is based on the cardiologist recommendation. Actually, after we observed the public data side and also the private data side, we found this is not our own finding. Actually, most of the patients who suffer from this AF, atrial fibrillation, they also have some other combined the symptom. Okay, so in this case, most of the existing research, they do like this simultaneous multi-labeling. Okay, they just do classification like AF or such other kind of heart arrhythmia. But for our research, in fact, we do the rapid decision support. Okay, we do the rapid decision support. What we do is that we just extract the features from both the public data side and the private data side, and extract the features for co-morbidity. Okay, the features. And then we try to derive we first do integration and reorganization of the data, and then we try to derive this RF risk. It's called a stratification mapping to just separate, to classify the risk level of the patient. For one example is that, if the patient suffer from the atrial fibrillation and also they noticed that the ST segment changes combined with the ischemic heart disease. Okay, so in this case, we just label as a high risk level, and then it will attract the physician's attention. Okay. Otherwise, if we classify as a non-high, we just wrote to the physician and to let them to review the process. Okay. So this plot actually are the screenshot for our AI engine. Okay. So the doctor can assess the plot and they can see the curves of the ECG signals. And they can do the analysis, and also they can see the digital report. So this is our ongoing research. Currently, we are working with the ECG device with the AI embedded AI, and also we do another Wi-Fi gateway, BLE gateway enabled data transmission. So in this case, the benefits for this study is that it can automatically obtain the ECG data. So this is our current research in this ECG-based AI. It's able to do pilot clinical trials at different hospitals, and this system has been granted international patents and results in more than 10 IEEE journal publications. Okay, so next I just try to let me see the time. Okay, so I just briefly explain our research in terms of the prediction. AF prediction. AF is atrial fibrillation. Actually, it's a common heart disease which affects 3 to 5% of the adults worldwide. Okay, and it's a serious problem. It can result in the stroke and sudden death. So actually it can negatively impact patients' health. And the current AF diagnosis method actually are mature, okay? But the prediction is still a challenging problem. So what's the benefits for the prediction? The benefit is that, so when the patient go to the hospital, okay, in a short time, might be they cannot detect they cannot obtain the ECG signal with the atrial fibrillation. Okay? Everything is normal, okay? So, but in fact, the patient, they suffer from this kind of atrial fibrillation, okay? But, if we have this prediction algorithm, so we can just, based on the obtained first maybe several minutes, we can just predict in the next 20 minutes whether there is a high risk for the atrial fibrillation, okay? So in this case, we can just ask the patient to come back, okay, at that time and then do the diagnosis. So this is the method which we used. We used the, 10 minutes ECG signal for prediction and to predict the possibility of the atrial fibrillation in the next 20 minutes. So we used the MIT BIH dataset, and also we just take the segments of 30 minutes with, the first 10 minutes they have no AF, but the rest of the 20 minutes they have the, AF or they haven't, okay? So we take the segments of those data. So this is the model, AF model. This is the artificial intelligence model which we introduced. So in the middle, this is a lightweight model, and we use the, CNN to try to capture the subtle ECG patterns, which is hard to be detected by human eyes. And also we use the LSTM, as a memory system to capture the signal changes over the time. Okay, by combination of these two, so we can not only to see the morphologic characteristics of the particular signal, we can also see the changes of this signal. So in that case, we can give a more accurate estimate prediction of the AF. These are the key results, and compared with some baseline models, due to the time limit, I did not go you, but it's published in a very famous journals, medical journals. Compared with the baseline model, our per model actually can improve the accuracy, precision, recall, and F1 scores. So the next one is about the Wi-Fi, but I'm afraid there is no enough time for me to discuss. So we do also Wi-Fi sensing, and so basically we just try to identify the activities in the indoor environment, and then we develop the machine learning, deep learning models to try to capture the models. And the last one, which I'm going to discuss, is about the pressure injury. Okay, so we developed a smart mat. Okay, the mat is used to measure the pressure distribution of a human being who are laying on the bed, and we use different methods and then to identify the pressure distributions, and also we collect more data and we develop the different models and to try to predict the positions of the of people who are lying down on the mat. And besides this, we also work with the breathing rate and also the heart rate monitoring. This is called vital sign monitoring, and this actually combined with worked together with the hospital, particularly for those people who has a mental health problem. Okay, so the last thing which I'm going to mention is about the future research directions. So in the future, so we plan to work on the segmented communications. Instead of transmitted data information, we transmit the meaning, as mentioned by Professor Branco. And also we worked in the hierarchical and the federated intelligence. Okay, so to work with the hierarchical, layer of the biomedical data. Okay, and also we developed the digital twins. Actually, we have already developed a digital twin for dementia predictions. And the next, we would like to work with this sustainable energy neutral IoT. This is based on the ambient backscatter communications. The power can be harvested from the ambient environment. The last one, which I listed here, is about the quantum and neuromorphic computing. We work with quantum sensing and quantum security IoT, and also neuromorphic computing, which is led by the brain activities, and we can, do the ultra low power and AI-enabled edge computing. Okay, thank you. This is the end of my talk. Thanks for listening.
Thank you so much, Associate Professor Zia Hoai-Lin, for your very insightful presentation. And now it's our honor to welcome the last speaker, Associate Professor Đặng Thế Ngọc from the Post and Telecommunication Institute of Technology of Vietnam. Today he will deliver a presentation titled Internet from the Sky, Connecting the Unconnected. Please join me in welcoming Associate Professor Đặng Thế Ngọc to the stage. Xin một tràng vỗ tay nồng nhiệt dành cho diễn giả của chúng ta.
Good morning, professors, lecturers, and students. My name is Đặng Thế Ngọc from Faculty of Telecommunications, and it's my great honor to be here today at PTIT. A very special place for us. Yeah. In PTIT, we have a good professor, we have a good student, and sometimes we have a good Wi-Fi. Do you think we have good Wi-Fi in PTIT? No? Yeah. If no, don't worry, we can connect internet from the sky. This is my topic of my presentation. Yeah, I would like to move the context. As we all know that internet is the infrastructure for the economic development, for digital transformation and digital government and many things. This is very important. However, we believe that in 2025, it means that in this year, there is still around 2.6 billion people worldwide still lack of internet access. This highlights a major digital device and impact on education, healthcare, and economic opportunities. So what's the reason that one half of population still cannot connect to internet? The main reason here is the geographical location. There are many areas in the world that we find difficulty to connect to the internet, such as in the mountain area, in the island, or in the forest. Recently, we also see many disaster areas, especially in Vietnam. This picture has been taken in Thái Nguyên city. We can see that one of the base station of Viettel is in a flash situation, and Viettel staff have to go into the base station to repair and recover the base station. And also in this month in Da Nang, many mobile phone customers lost a signal for the long time during floods. This wise we can maintain the internet access for everyone. On the other hand, the requirement for 6G is, as we may know, that besides the requirement of high data rate, low latency, high reliability, massive connectivity, and energy cost, one of the challenges here is extreme coverage. 6G needs to bring gigabit per second coverage to everywhere. Not only for the user on the ground, but also nowadays we see a lot of vehicles in the sky, such as UAV, plane, or loon, and satellite. So one of the requirements of 6G here is need to provide the connection in the sky, in the space, and even under the sea. Here's the solution. We can see that we can use various vehicles to provide the connection from the sky, such as satellite in the space, and also high altitude platform and UAV. Actually, satellite communication is not new idea. It appears already 70 years ago. The first one, artificial satellite, namely Sputnik, was launched and opened a chapter for satellite communication. Recently, we host many satellite projects from the famous company such as SpaceX, Amazon, and OneApp that have been developed satellite constellation to provide internet access over the world. Different kind of satellite orbits can be used. For the geostationary orbit, this altitude is a little bit high, far from Earth, at the altitude of 36,000 kilometers. The use of geostation orbit have the disadvantage of the round trip propagation delay. That's why now people are interested in low Earth orbit, which operates near the Earth, and the round trips reduced to around 1 millisecond. However, we need more satellite to cover the Earth because the visibility of each satellite is lesser than 15 minutes. So the conclusion here is satellites are considered provide global connectivity, especially for the remote, rural, disaster area, thanks to their wide coverage area. Besides the application of provide internet access, satellite can be used for many types of applications, such as disaster relief, IoT connectivity, weather prediction, and especially it can provide access when people on the ship or on the plane. For the last mile access satellite system still based on radio frequency band. For example, Starlink projects use KU band with the frequency from 12 to 13 gigahertz, offers the data rate of 50 to 150 megabit per second. However, in the future, especially for the 6G, the satellite communication need to meet the requirement of gigabit per second transmission, and also the RF spectrum are congested, so we need to shift to higher frequency. In higher frequency, we can based on optical carrier to carry the data instead of using radio frequency. So free space optical in short MSO laser comm could be promising candidate. We can deploy MSO in various scenarios. For example, we can use MSO to connect inter-satellite. Actually, it's in Starlink, inter-satellite laser link are setting new records with 42 million gigabytes per second in last year. We also use satellite to MLOs to connect satellite to SAP, satellite to UAV, and also satellite to ground station. For the different type of scenario, we have different type of challenges. For example, in the second case, beam misalignment is the main challenging issue due to the long transmission distance. However, when you transmit the signal, the optical signal from satellite to UAV or to ground station, weather effects will be the biggest challenging issue. Why weather is the biggest challenge? Because this kind of vertical MSO link, it will go to various altitude, and here cloud may block the MSO beam. However, the study on the impacts of cloud coverage have not been guideline in detail, and this is our mission to explore and study on the effects of cloud. Actually, the Earth's surface is 50% covered by cloud, and there are three types of cloud coverage: the high-level cloud, middle-level cloud, and low-level clouds. For the cloud at low level, its particle and the FSO wavelength have almost the same size. So my scattering theory is possible for express the attenuation in terms of cloud liquid water content. So what is the problem statement here? As you can see in 4 cities in Japan, in Vietnam, each city and each country have a different distribution of cloud liquid water content. So before setting up the MSO system, we need to carefully consider the cloud level in each location and each time of the year, so that we can have the reliable communication MSO system in the effect of cloud. And here's how Japan analyze the cloud level. They, based on the site diversity, implement around Japan. And each side you can see that they have the whole sky camera. They use the whole sky camera and other information such as humidity, pressure, temperature to estimate the size and the height of the cloud, which is the information for the system design. However, this method have a disadvantage of complex hardware implementation and cost is expensive. This method is not suitable for developing countries like in Vietnam. So we will propose announce the method to estimate the cloud level. Here we will based on the data of cloud liquid water content that's obtained from the satellite database provided free by European Center for Medium Range Weather Forecast. We also, based on the model that different from on-off model channel, that FSO link will be blocked whenever there is a presence of a cloud. Actually, FSO link can still maintain with the low cloud or liquid water content. So here we will, based on the data of the cloud liquid water content, and then we estimate the probability distribution of cloud water content, and then we can get the value of attenuation. Here is an example, the location in Japan. We collect the data for 5 years, 24 times per day as altitude from 1 to 3 kilometers. Resolution is 10 kilometer by 10 kilometer. Our goal is to provide the accurate estimation model for MSO by satellite link availability, and also we propose using site diversity to improve the availability. This is our result. We have collected the data, and then we plot the map for 47 cities in Japan. With the link budget is 30 dB, and we can see that here Hokkaido have the highest availability in the rainy season. This is because in rainy season from June to July, there is no rain in Hokkaido, and also the cloud liquid water content is small, and we have the high availability. We also do the same in Vietnam for Hanoi, Da Nang, and Ho Chi Minh City. In 4 seasons, spring, summer, and autumn, winter, and we can get different value of availability. And by using the site diversity, for example, we use 2 sites, one in Hanoi and one in Da Nang. We can improve the availability into 96.8%. In this case, if the cloud blocks the link between satellite to Hanoi, and then we can move to get the signal in Da Nang and vice versa. And if we combine three sites, Hanoi, Da Nang, and Ho Chi Minh City, we can increase the availability into 99%. And this information is very useful for FSO design. This because we have applied and got the sponsor from Asia Pacific Network Information Center to do very new project. Start from next year. We will deploy our model to at least 10 countries in Asia Pacific region, so that we can give the recommendation for other government to apply our model for the design MAO system. Other methods here to avoid the impact of the cloud is we combine many levels, many types of vehicle. For example, here, if the FSO link from satellite to HAP and to the ground station is blocked by cloud, we can use optical intelligent recoverable surface at UAV to reflect the optical beam to the ground station, and we can avoid the impact of cloud. We also have one project that combine optical IRS with wireless power transfer, so that we can charge the UAV via optical beam. We also apply our model to the quantum key distribution. Actually, quantum key distribution is received more interest recently. China has successfully established a QKD system that developed key from China to Europe. So it's about our topic here. We also apply AI and ML to improve the performance and improve the efficiency of resource for the non-terrestrial system. So here is my conclusions. Non-terrestrial and terrestrial network are converging in 6G with the name of space, air, ground integrated network. And in overall non-terrestrial network, not just coverage extension. NTN is the core pillar for achieve UBT code, low latency, energy efficient, and accessible 6G network. And I would like to finish my presentation. Thank you for attention.
Thank you so much, Associate Professor Đặng Thế Ngọc, for those insightful perspectives. Ladies and gentlemen, and now we move on to the panel discussion, the most interactive part of today's program. For our online audience, please feel free to submit your questions in the chat box, and we will direct them to the most suitable speaker. And for those of you who are joining us here in person, simply raise your hand and we will bring a microphone to you so you can ask your question directly. To begin our discussion, may I invite our moderator, Dr. Nguyễn Việt Hưng, Deputy Head of Department of Science, Technology Management and International Cooperation, to the stage. And now may I also invite our distinguished speakers to join us on the stage for the discussion. Please welcome Professor Branka Vucetić, Associate Professor Dì Hoài Linh, and Associate Professor Đặng Thế Ngọc to back to the stage for this panel discussion. Xin một tràng vỗ tay nồng nhiệt dành cho các diễn giả của chúng ta.
We begin our panel talk session. Thank you all all the distinguished speaker for your very informative talk today. So my first question for Professor Branca. In your talk, you said that in beyond channel communication, we will use AI model to replace the channel block. So AI model offer many advantage, but it's also increased a lot of computational demand and processing time, and also for implement every block and changes to AI will cost a lot of, it will make a lot of challenge. So in your opinion, what is the biggest obstacle in real industry to adopt the AI model for communication?
Yeah, thank you very much for your question. So in applying AI methods, as I said, they have many advantages, but the biggest shortcoming is that a huge amount of computational power, data is required to train them. In particular, those generic neural networks like fully connected neural networks or convolutional neural networks or recursive neural networks. So this is particularly relevant to the future networks, which will be heterogeneous, which will have a large number of nodes, a large number of users, and as I said, they generate data of very high dimensionality. So dimensionality means that each antenna, each user, each time slot, each code word adds that dimensionality, and then the training complexity becomes exponential. So you need to train them across all signal-to-noise ratio, across all users, across all antennas at the base station, across all code word lengths. And so this is impossible to achieve. So I guess that is the main obstacle to applying them now in real time. And so it needs to wait to the time when we have enough data and enough computation power to do it. It's expensive. It requires a lot of energy.
So I can recap that in order to achieve that future, we still have many research in order to compress the data, aggregate all the data, and also new training method to get to that.
To process that and combine with analytical methods. So if you were just to remember one thought from my talk, it is that you cannot use AI alone.
Okay.
You have to use it with analytical methods for many reasons. But the main one is to prevent hallucination of AI.
Yeah. So a lot of our students down there, they are from the Telecommunications faculty and also for the professor. So this will, I'm sure that this will open a new research direction for them, because for now we have the computer science faculty, which very specialized in AI. We also have AI faculty, and also we have telecommunication faculty, which very deeply into telecommunications. So now they will merge together. I think, yeah. Okay. Thank you very much. And our next question, I will take this to Professor Jihai. So in your talk presentation, you give us a lot of information about smart healthcare IoT service and system like ECG and IoT smart mask, something like that, to apply in medical and hospital. But one problem is that for the AI or smart device to be trusted and officially certified for medical use, here in Vietnam we often have to have the committee of medical ethnic improvement. So that process is quite hard. So how do you get all the validation requirement or regulatory allow to get this device into the real hospital application?
Okay, so in terms of your question is related with the regulatory compliance and also the clinical trials, right, at the various hospitals. So we, in fact, we worked, because we are a faculty of engineering, actually we have a very close collaboration with the faculty of medicine and health. And we have teaching hospitals in the University of Sydney. And so we collaborate with colleagues from the Faculty of Medicine and Health, and also the physicians, cardiologists from the West Mid Hospital, the teaching hospital in the Faculty of Medicine and Health, and then we follow the the regulatory compliance against the device clinical trials. So basically this is the one we're trying to see. Yeah.
Okay, so I guess that your advantage is that in the University of Sydney you have medical faculty, or I can say you teach medical hospitals also in University of Sydney, so that you can join research with them directly in.
That's true.
Yeah.
That's true.
Okay, so that's a very big advantage. Here we have separate university from medicine, so so I guess that we have to connect with them because in our faculty we have a lot of research about ECG also. Yeah, but to get it into the medical trial is very hard. Okay. So thank you very much. And my next question, would like to ask the Associate Professor Đặng Thế Ngọc. So in your conclusion, you said that the shift toward a unified space, air, ground integrated network or end-to-end network will playing a key role in 6G. But the problem is that now we see that with the satellite communication system, there will be delay and some kind of difficult to transfer the data between different systems like satellite, UAV, ground station, and then to the mobile network. So there will be a big challenge in terms of efficiency and also the delay. So how do you imagine that we can bypass this challenge in the 6G or the next generation of communication?
Thanks, Dr. Hưng. Your question is very interesting and very challenging. Actually, in my opinion, we need to classify the service and deploy the computing in different level. Even on the UAV, we deploy AI chip to process the small text that require low latency, and for the higher level at HAP or satellite, we can deploy the data center, maybe small data center. Maybe 2 days ago, I heard that China have tried to deploy data center on the satellite, so that different missions can process by different level of computing. So the processing as the UAV lasts like the mobile edge computing, and it can support the vehicle and critical mission. And for the mission that requires large ability of processing, you can go to the sky or even go back to the ground station, and then we can solve the problem. Thank you.
Okay, so I understand that it's kind of similar to edge computing now, right? So that would be a huge effort in synchronize and control all the different part of the communication system, and that will lead to your future work, right? To cooperate all the system together, and then that will serve the infrastructure for all your application now in IoT and stuff. Okay, so thank you very much. And now I looking at the audience. Do you have any question for our speaker today? Please raise your hand. Raise your hand. I'm sure that we have learned a lot today. Yes.
Miss Chang.
So we have the supporter, please.
Good morning, professors. We are very thankful today to hear very new information, new direction in the research. Yeah, it's very valuable for us. Yeah, I'm a teacher. I'm a lecturer in the telecommunications of PTIT. Yeah, and today I have a small question about the first presentation. It's very interesting for me about the semantic communication. Yeah, I see that you have some very valuable, very great results. And I have a small question about the. I think that the segmentation scheme. Because beyond the semantics, so you have some segmentation scheme for the research. So how can you explain a little about the segmentation scheme affect to the system performance of real research?
Okay, thank you. For
maybe for example, I think that the single you divide the semantics word by words or something like that. Maybe it's affect to the results. So can you explain something about the segmentation scheme you use? Thank you.
Okay, thank you very much. So can you hear me?
Yes, I can hear you.
So the segmentation is based on meaning. So we used a large language model for the segmentation and semantic error control coding.
Okay.
So in the example that we showed, we separate the words in a sentence and of a certain length. And then if the words are smaller, then we put, for example, a couple of words to have the same length. So if the length is not exactly the same, we pad it with zeros in the end. So in order to have the same length, and the reason to have same length is to form short messages, which we then protect by short channel codes. So the key word here is short instead of long. So short block codes in order to avoid these fatal decoding errors which affect the whole block. So if there is a fatal error, it affects a small block and then it remains enough semantic context to recover the whole sequence, the whole sentence. So what we do first, we do the segmentation into short, meaningful blocks like words. Then we do a block short channel code encoding in parallel to reduce latency. Then we transmit it over the channel. Then we have first the channel decoding of parallel short code words, channel codes decoding of short blocks. And after that, we have semantic decoding by using this large language model bar. So that means we have combined channel decoding and semantic decoding. And so that's why it achieves better performance. But the key here is don't use long codes because they don't give good performance. Use short codes, which is quite opposite from the traditional systems where we said it's good to use long codes because they have high error correcting capability. And by doing this, we even achieve low latency than with traditional long codes because of the parallel processing, and the large language model, even though it gives some overhead, still when you add latency of the channel decoder and the large language model, it is still lower than the latency of long block codes in traditional communications.
Yeah, okay. Yeah, thank you. So I heard, so we know that, so here it does use the short code. So it can improve the performance compared with the good segmentation scheme, right? Oh, thank you, President.
That's right. And it can improve the performance not much at the bit level when we use block error rate to compare the performance, but when we use the rouge, which is the semantic criterion for performance, then it is significantly improved.
Yes. So it's improved because of the segmentation when we
segmentation
recovery.
And short codes.
Yeah. Thank you. So very nice. Thank you. And one more question, please. A small question. Now we have many model language model. So to pay on that, you design the segmentation scheme, right? Yeah. So
large language model, BART.
Yeah. So maybe the how can I say? Do you have any survey about the model language good for English or something like that for the?
So there are different large language models like Gemini.
Or other language. There are, but here we use it because it suits our application. So for different application, we use a different model. For example, for images, we use MU3, which is visual tokenization. So you just need to adjust. Of course, you can use it, but then it gets high latency, and you don't need that power. So you use a less powerful large language models, which are adjusted to this application.
Okay, thank you very much. Thank you. Very nice.
Thank you.
Thank you, Professor. And I have a signal that we ran out of time, so maybe we have one question for our student. That's when we, because let me say that the University of Sydney is ranked first, or the top university in Australia. So this will be the very good opportunity to our students to present ourselves, and maybe there will be the opportunity for you to go visit the University of Sydney. This year, last year and the year before that, we already sent 2 big group of students to University of Sydney to take part in the coding fest, and they all had very high ranking and high prize. So for our student in the audience, do you have a question? Okay.
Hello everyone, my name is Tu Chang, and I'm currently a third-year student at PTIT, and I would like to ask the professor questions. My question is, are there opportunities for PTIT students to participate in research projects, exchange program, or collaborative process in the near future with university in Australia in general, and especially in University of Sydney?
So I guess your question is that is there a chance for exchange student collaborative research in Australia in general, and also in the University of Sydney, especially for the student?
In general, these exchange programs are done through joint PhD programs. So there is possibly opportunity in the future to establish a joint program. But in the meantime, we can do it only through the collaboration between supervisors. So if the supervisors at the University of Sydney establish collaboration with professors, academics here at PTIT, and if we are working on similar research areas, then it is welcome for students to come to spend some time at the University of Sydney, and vice versa. So in principle that is feasible, but I believe that this meeting and this event could be just a beginning of such collaboration.
Okay, maybe I can just mention something. Because we conduct research and also teaching, so in fact we have quite many students from Vietnam and study in our engineering faculty. So I think this might be, I don't know whether this comes from this exchange program or just the personal behavior, but in fact, we have quite many research collaborations with different researchers all over the world. So if you're interested, might be you can just maybe send an email to the supervisors which you are interested to work with to ask. Might be this there is some opportunities depends on the individuals of the supervisors. Yeah. Okay. Thank you.
So I guess that the answer of the professor of University of Sydney here is that for now, in the very near direction, is that you can join the research group of our professor here. With the new direction here, you can see that on the presentation of our speaker. And then when your supervisor or the professor of PTIT accept you in the research group, you can improve yourself, and then we can connect with University of Sydney for the exchange research. That is the very near future. But as PTIT, I'm sure that the director board of PTIT are push for the longer cooperation between PTIT and University of Sydney. So maybe there will be an exchange program of 2+2 in the near future. And also you can say that we can have internship or for final project thesis in the University of Sydney. So today is a starting point, and I hope that in the very near future we will have a lot of PTIT students to visit and study in University of Sydney. So thank you very much for your question. Yeah. And with this, I'm sure that we still have a lot of questions. I have all the presentation from our speaker today and all the contact from our presenter today. So if you have any question, you can contact me or directly with the professor here, right? After this workshop or this meeting. So thank you very much, Professor, for coming today. Thank you, Professor Ngọc, for your hospitality, because he's in Faculty of Telecommunications. And with this, I conclude the panel talk.
Thank you so much, Associate Professor Đặng Thế Ngọc and our distinguished speakers for this very interactful program. And ladies and gentlemen, so with that we have come to the conclusion of today's event. May I kindly invite you to return for your seats, because now we are closing our event today. Thank you so much again. Ladies and gentlemen, and with that we have come to the conclusions of today's InnovaConnect event. On behalf of the VinFuture Foundation and the Post and Telecommunication Institute of Technology, we would like to sincerely thank all our speakers, distinguished guests, and participants for joining us today. And before we close, a quick reminder, the nomination for the 2026 VinFuture Prize are now open, and we invite you all to contribute to recognizing groundbreaking innovations that improve lives worldwide. For further information on how to nominate for the 2026 VinFuture Prize, please visit our website at www.vinfutureprize.org. We are also pleased to share that this December, the Foundation will proudly host the 5th VinFuture Prize Award ceremony, marking 5 remarkable years of honoring science for humanity. Alongside the ceremony, the Foundation will organize the VinFuture Science and Technology Week in early December, featuring a series of inspiring scientific networking activities where we will have a chance to meet and connect and learn from leading scientists and innovators around the world. We invite you to follow VinFuture Prize on Facebook, LinkedIn, and other social media to update the latest news. Once again, thank you for joining us today. We look forward to seeing you in our next session. We wish you a good rest of the day. Xin cảm ơn mọi người ạ.